Today I'm going to finish up this unit with a discussion of valence bond theory and hybridization of orbitals. The basis for valence bond theory is that valence electrons in the atoms are what participate in the bonds, and so they are found in atomic orbitals. And since chemical bonds result from an overlap between two orbitals that are half full in a covalent bond, that the geometry would be determined by the geometry of those overlapping orbitals. So let's take a look at how well that theory holds up. So for a molecule like H2S, what we would expect that H2S would look like is that we have sulfur, and we have a hydrogen, and another hydrogen, and then we have two lone pairs on the sulfur. Okay, and so based on where the orbitals are for all of these things, the four orbitals that the electrons are in the sulfur are going to be an s orbital and three p orbitals. And so if you remember, the p orbitals, which are shown in red over here, they go one up and down, one side to side like this, and then the other one is in the z axis, so it would be coming in and out of the board, so sort of out like this and back like that. It's hard to draw, okay? And so if that's where all the electrons are, and then also one in the S, sorry, forgot about that one. And so if that's where they are, then if the hydrogens are going to overlap with two of the p orbitals, so if that's one hydrogen and this is one hydrogen, then the angle we would predict would be 90 degrees, because that's the angle between the p orbitals that the valence electrons are found in. All right, and if we measure that bond angle in the actual molecule, we get an angle of 92 degrees. So that's actually not so bad in terms of prediction. But now let's look at a molecule like methane. So for methane, we have carbon, which has four hydrogens around it. And each of those each of the valence electrons would be in a p orbital, and each of the hydrogens would have an s orbital with one electron in it. So again, if we were to draw a couple of them, we would get one over here, one electron from the hydrogen and one from the carbon. Same thing here, one from the hydrogen, one from the carbon. And so the predicted bond angle between those two, again, would be 90 degrees, because that's the bond angle between the p orbitals. But what we actually get is an angle of 109.5. So valence bond theory is different than VSEPR, which is what I talked about in the last video. VSEPR is based purely on geometries and electron repulsions. Valence bond theory takes into account where the electrons are in the orbitals. And so it does a good job in the case of SH2, but in general, it doesn't do that good a job, which is what we're seeing here with methane. And so we need to modify this theory just a little bit. And the way we modify this is through a concept called hybridization. And orbital hybridization is basically just a recognition that the orbitals in an atom are not exactly the same as the orbitals in a molecule. And so hybridization is a mathematical procedure in which the standard atomic orbitals, these are the s and the p and the d that we've talked about, are combined to form new atomic orbitals that we call hybrid orbitals. So the hybrid orbitals are the result of hybridization. So they're the combination of the atomic orbitals being recombined mathematically to generate these new orbitals that we use in molecules. So let's revisit methane with this new component of valence bond theory. So the valence electrons in carbon are found in the 2s and the 2p orbitals, okay? And so if we were to take all of those four orbitals and recombine them so that we get new orbitals that are all identical, that all are equal in energy, that process is hybridization, and the orbitals that we get out are called sp3, and that's because we used one s orbital and three p orbitals in order to get them. So you can think of it as like s to the 1, but we don't write that, and then p to the 3. So spp gives you sp3. Okay, and then these new orbitals are all identical in energy, and it turns out that when we do that, they give us this new shape that we have here. So instead of the S and the P, so if you remember the P orbital, one of them would have looked like this, one looks like this, one's coming out of the screen and back in at you, and the S is like this. Okay, that's what we looked at on the previous slide. When you recombine them, you end up with 4 orbitals that have uneven lobes, so they are really big on one side and small on the other, and they form a tetrahedron because you have 4 of them, and then one's coming back out that way. Because you have 4 of them that are identical, and because of electron repulsion, you want to get them as far apart as possible. So each of those, and it's shown much better over here in purple, so each of those can hold one of those 4 valence electrons, and then hydrogen doesn't have to hybridize because all of its electrons are in one orbital anyway. And so you just get overlap between the 1s orbital in hydrogen and the sp3 hybrid orbital in carbon. And anytime you have a carbon atom that is going to form 4 bonds using these 4 valence electrons, this is the hybridization that it will use. Now let's take a look at ethene. So ethene, if we were to draw out the Lewis structure, has a double bond, and then we have off of each carbon we have 2 more hydrogens. So that's where we get the C2H4 from. Okay, so each of these carbons only is going to make 3 bonds because one of them is a double bond. And so the hybridization is going to look a little bit different here because we don't need to overlap with 4 atoms, we only need to overlap with 3. And so as a result, we're only going to hybridize with one of the 1s orbital, or the 2s orbital, and 2 of the 2p orbitals. So that's going to give us an sp2 hybrid because we're only using 2 of the 3 2p orbitals. Okay, and then that leaves one of the 2p orbitals unhybridized. So it's a little bit higher in energy, but we don't need it because it's not going to be involved in a bond. And so one thing to notice that I didn't mention on the previous slide is the hybrid orbitals are always going to be in between the energy of the 2s and the 2p because we've mixed them together. So higher than what the 2s was, but lower than the 2p. All right, so when we do that, we get similar shaped orbitals, but now they're going to be in a triangle instead of in a tetrahedron. Sorry, that's not the best picture, but you can see them up here in purple, drawn much better. And so for, let's just take a look at this carbon to start with. So it overlaps with the 1s orbital and the hydrogen here and here. And then the last sp2 hybrid orbital is going to overlap with the sp2 hybrid orbital of the other carbon. And now this p orbital that is left is going to be sticking above and below the plane here and here. Okay? And so we're going to be able to get overlap of that orbital above and below the plane of the molecule, which is what gives us our double bond. So that is where those last electrons are shared because they have to be shared between the 2 carbons and we don't have room for them in our hybrid orbital here. So they're here and here. And remember that the electron is not a particle in one place, it's in a cloud. So that cloud is both above and below the other one. And that gives us that additional strength, pulls them a little bit closer together because we have that extra bond. So another piece of terminology that we should discuss are sigma bonds and pi bonds. So a sigma bond is one that the overlap is directly between the 2 atoms. So the purple overlap here in the ethene molecule represents a sigma bond because it's just direct overlap, and all of the bonds in methane that we looked at on the previous slide, those are all sigma bonds, and the CH bonds in this molecule are also sigma bonds. The pi bond is the bond that's above and below the plane in the double bond. So just to refresh or sum up, a sigma bond is a result of 2 atoms or 2 orbitals overlapping end to end, which is what we always get in a single bond. And a pi bond is a result of p orbitals overlapping side by side, which is what we have in double bond, and we're going to see in just a minute is what we have in a triple bond as well. All right, last but certainly not least, we have sp hybridization. So if we draw the structure of ethine, we have carbon with a triple bond to another carbon, and then they each have one hydrogen coming off of them. Okay, so in this case, we're only going to hybridize the 2s with one of the 2p orbitals. Okay, so these, again, have a similar shape. If our carbon is here, we have one like this, and then we have one like this. So they look very similar to the p orbitals, but they are have uneven lobes. So you get a big lobe on one side and a teeny lobe on the other with each of the hybrid orbitals. Okay, so for a particular carbon, so if this was this carbon here, then the hydrogen would be here with its 1s orbital, and the overlap would be there, and the electrons would be here in the middle. And then the other carbon over here is going to have, again, sp hybridization, and the electrons are going to overlap in the middle there, and then with the other hydrogen over here. Okay, now we have two p orbitals that are left over, and it's really hard for me to draw them in 3 dimensions, but you can see them here. So we had one that was like this left over in this carbon, and then we had one that's coming sort of in and out of the board that's left over, and then the same thing over here. Okay, and then you get an overlap above and below, and then on either side of the carbon-carbon bond. Okay, so in this case, we have one sigma bond that's represented by what I drew here, and it's represented by the electrons in purple up there. And then we have two pi bonds, one from each of the two p orbitals that are left in each of the carbons. And that's what gives us a triple bond that we have in ethine here. So now that I've told you all this, how do we use this information? And so basically, the way you're going to figure out what the hybridization is just by looking at how many electron groups are off of a given atom. So in this example, we're looking specifically at carbon, and this is where this hybridization model is used the most. Organic chemists use it a lot, and organic chemistry is just the study of molecules that are composed mostly of carbon. And so that's why this is so useful here. So let's take a look at these molecules. So for this carbon, we have 3 things attached. We have an oxygen up here, we have a carbon over there, and we have an oxygen over here. Okay, it doesn't matter that the oxygen up here on top is a double bond. We're just looking at the number of electron groups. Okay, so since this needs to bond with 3 different things, we're going to have an sp2 hybridization. Okay, which leaves one p orbital left, and that p orbital is going to overlap with the p orbital in the oxygen and form another pi bond, which is what's going to give us our double bond. Okay, now let's take a look at this carbon here. All right, this one is forming 4 bonds, so we need to use all of our s and p orbitals to make hybrids, and so this is going to be sp3 hybridized. Sorry, the 3 is not very nice. Okay, and then the same thing with this carbon here. We've got 4 bonds, so this is also going to be sp3 hybridized. Okay, over here we have this carbon is making bonds with 3 atoms. Okay, so it's going to be sp2. This carbon here is making 3 bonds, so it's also going to be sp2. sp2. And this carbon here, again, 3 bonds, also sp2. Okay, and we didn't look at an example where we had something like oxygen, but I'm just going to do one real quick. So let's say we have water, all right, which looks like that. All right, this has 2 bonds, but it has 3 electron groups. So oxygen is going to need to use all of its orbitals in order to make hybrids. So this is going to be sp3 hybridized. And 2 of those orbitals, which is going to give us 4 hybrid orbitals, and 2 of them will be used to bond with the hydrogens, and the other 2 will be used to house the lone pairs that are on there, which is how that oxygen has a tetrahedral electron geometry, and how we get bent for the molecular shape. All right, so this sums this up. We're going to look at some of these in Mastering Chemistry and do a little bit of practice, but hopefully you have a good sense of why we need hybrid orbitals and how you can determine what the hybridization is going to be based on how many electron groups are coming off of the atom.